Ananda, can you just check whether the live stream is working or not? Is the live stream working, Ananya?
Checking it.
Okay, so let me check also. Is the live stream working, Ananya?
वंडरफुल गया नहीं बहुत शक्तिशाली हो गया
1 minute, I'm just checking. Is the live working, Ananya?
Yes, sir. Now it is working.
Okay. So we shall start within next 2 minutes. So I'm checking.
बहुत शक्तिशाली हो गया
Okay, it's working. Is the live working, Ananya?
Shantanu sir, I request you if you can mute the YouTube live stream, otherwise the voice would glitch.
Yeah,
As the voice would repeat.
yeah. Actually, I stopped it and just I was checking whether it was working or not. Okay, it's fine. Uh, Dr. Tyagi, can we start?
Yes,
Dr.
yeah, I think we can
Oh,
start.
okay. So, Honorable President of Indian National Science Academy, Professor S.C. Mandesar, Honorable Chair of the Indian National Young Academy of Science, Dr. Mohit Tyagi, distinguished fellows and members of INSA and INYAS, eminent personalities from industry and academia, esteemed guests, dear research scholars and students, good evening to all of you. It's my great pleasure to warmly welcome you all to this INYAS Distinguished Lecture on Artificial Intelligence, organized by the Indian National Young Academy of Sciences under the aegis of the Indian National Science Academy, New Delhi. We are deeply honored to have with us Professor Jeffrey David Ullman, Emeritus Professor from the Department of Computer Science, Stanford University, USA, as the distinguished speaker for this lecture. We sincerely thank Professor Ullman for graciously accepting our invitation and for joining us today. On behalf of INSA and INIAS, it is indeed a matter of great pride to witness such an overwhelming response to this online lecture. We have received more than 202 registrations from participants across various institutes in India and abroad. The event has attracted significant interest from eminent academicians, including fellows of various scientific academies in India, scientists, students from prestigious institutes such as Raman Research Institute, IITs, ISERs, various CSIR laboratories, various ICAR institutions, Vigyan Foundation for Science, Technology and Research, central, state, and various private universities, various state-funded colleges, etc., as well as international institutions, including University of California, Davis, SSBM, Geneva, We are equally delighted to note the interest shown by several personalities from the various industry sectors of India. With these words, I once again extend my heartfelt welcome to all of you. I hope this session will be insightful, engaging, and enriching for everyone. Thank you. Now, I would like to request Professor Shekhar C. Mandesar, President of INSA, for delivering his valuable opening remark for this program. Sir, over to you.
Thank you, Shantanu. A very warm welcome to all of you. Uh, Warm welcome to Jeff Pullman. I met Jeff when he used to come to Hyderabad to the Tata Consultancy Services on the advisory board. And it's very early in the morning. So thank you, Jeff, for joining. But welcome all the colleagues. Welcome all the colleagues online to have joined. As all of you are aware, Indian National Science Academy, INSA, is the premier science academy of the country. And it's a very exclusive club of scientists. But among the many things that INSA does is also promotes science among the younger scientists. And that's how the idea of Indian National Young Academy of Sciences that emerged, which INSA mentors. And like every time I say, we are incredibly proud of our younger generation who have been very active and have held several programs such as this in the past. And your engagement with society in science in general, but otherwise all the programs that you have been conducting at multiple places through your local chapters and otherwise is greatly appreciated by the senior scientific community of the country. And I do wish that you go a long way in promoting the culture of science and technology in India and in our society in general. Very warm welcome to Jeff. As again, as I said, I met Jeff when he used to come to Tata Consultancy Services through my wife, who is sitting to my left. She was working on TCS then and has had the advantage of having his guidance on multiple programs. So, very warm welcome once again from the side of Indian National Science Academy. And I'm sure, as Shantanu said, it will be a very deep, engaging session in the next 1 hour or so. Over to you, Shantanu.
Thank you, sir, for your very informative opening remarks. Now, I'd like to request Dr. Mohit Tyagi, Chair of Indian National Young Academy of Science, to uh, introduce the INYAS to our audience as well as our esteemed speaker, Professor Jeff Pullman. Over to you, Dr. Tyagi.
Thank you, Dr. Santanu. Ananya, can you enable sharing so that I can share? Santanu. Yeah, very good evening to all and good morning to Professor Ullman. And it's my great privilege and my duty to introduce INYAS in front of such that distinguished audience. So, respected President INSA and other INSA fellows and my INYAS colleagues. So I'll just share a few slides. I know that we all are waiting to listen the talk from Professor Ullman. So I'll just take 5 minutes to introduce INYAS, Indian National Young Academy of Science. I hope my presentation is visible to all.
Yes, sir, it is visible.
So Indian National Young Academy of Science INYAS, it was established by INSA in 2014. So initially INSA Council selected 20 members, and then every year new membership applications are there and members are selected. So currently the structure of INYAS is like
Your
there
Zoom
is
screen
one.
is visible, sir.
Dr.
Yeah.
Tyagi, your screen is not visible.
Your Zoom screen is
Oh,
visible, sir.
oh, presentation is not visible. Is it visible now? My presentation?
No.
Sir.
Mm,
Sir, you share your entire screen and then go to the presentation
Yeah,
section.
yeah. I was saying this.
Now
Yeah,
it
Is it
is.
it's
visible
now
now?
it's now it is visible.
Okay. So this structure of INYAS currently is one chairperson and tenure is 2 years, and chair is elected by INYAS members. And then there are eight core committee members representing different science disciplines like physical science, chemistry, biological science, and there are also tenure is 2 years. And then we are having 119 currently members. So every year we select few members, and the success rate is really very competitive. We can see that success rate of 2025 membership was 5% only. 24 members were selected. And then tenure of INYAS membership is also only for 5 years. So after 5 years, members become alumni, so that the academy always be young. And there are around 147 alumni members are there. So with these members and alumni, we are covering around 200 institutes all over India. So it shows that our diversity and then our networking all over institutes all over India. So our President INSA also told that our mission is in line with the mandate of INSA. So we always want to engage in interdisciplinary and intergeneration dialogues on scientific issues with very vision. We are involved in the promotion of science education, so with different outreach events. Then networking among young scientists, which really goes long, very long way. And then we are developing scientific temperament among young scientists. Then we are supporting them for career development with various events. So, and then we are having collaborations with other young academies like Global Young Academies or IPA or International Science Councils or other Asian Young Academies. So many other young academies. We are having collaborations and we do conduct various events in that collaboration. So if we see the geographical distribution of members since that inception of INYAS, so we can see that we are covering all over India, starting from north to south, east to west, from everywhere, from all institutes, we are having the members, and we are INYAS is currently divided into 10 chapters. So we can see that almost we are having representation from all zones, all chapters. Then if we see the subject specific, so members and alumni, we are having different disciplines like chemical science, agricultural science, engineering science, and we are maintaining good gender balance, also having about 30% women scientists. So this is just a glimpse of our events. Then every month we are conducting about 10, more than 10 events, and which are mainly covering science competitions, meetings, flagship events, outreach events. We are having some policy related events, white papers, develop, maintaining this national task forces, and then some publications, special issues of publications, either some women in science domain specific or some subject specific. And these competitions are also for this science awareness, they are very popular, like Saransh, which is 3 minute thesis presentation every year. More than 300, 500 students usually take participants. PhD students are there for national competition for research excellence and science art. So we engage so many research students and try to spread this science awareness. We are having remote area lectures covering very remote areas from the northeast, Jammu Kashmir, Ladakh, and different places of India. And we are conducting various science awareness camps. And with just this glimpse, I'm really very thankful to INSA for continuous support. So, with the guidance and mentorship of INSA, we are able to conduct all those events. So, we are now currently, that is our core committee, and we can see this gender balance in core committee also. Out of eight, five women are there. So, we are very thankful for our women in INYAS also. So, with this, I'll just stop this because we all are waiting to listen, Professor Ullman. So over to you, Santanu. I'll just
Okay.
stop sharing.
Thank you, Dr. Tyagi. Thank you for your brief introduction of the INYAS to our audience. Now, it's my pleasure to introduce Professor Jeffrey Ullman, today's distinguished speaker, to all of our participants and dignitaries. So, Professor Jeffrey David Ullman was born in the year 1942. So, he is a distinguished American computer scientist renowned for his foundational contributions to database systems, automata theory, and algorithms. He earned his BS from Columbia University 1963 in engineering mathematics and PhD from Princeton University 1966. He began his career at Bell Laboratories and later served as professor at Princeton University and Stanford University, where he also chaired the computer science department. He is currently emeritus professor at Stanford and CEO of Gradients Corporation. Professor Ullman is a member of prestigious bodies such as the National Academy of Engineering and National Academy of Science, USA. He is a fellow of ACM. His numerous honors include the prestigious AM Turing Award that he was bestowed with in the year 2020, Knuth Award in 2000, IEEE John von Neumann Medal in 2010. He was authored over 200 research papers and 16 influential books, including the classic Introduction to Automata Theory, Languages, and Computation, and various others, which have shaped the modern computer science and education and research. Now, I'm requesting Professor Ullman to deliver his valuable talk. Professor Ullman, over to you.
Right. Well, thank you very, very much. Okay, I'm really, this seems like a great organization. I congratulate all of the members of this young academy. Um, anyway, I am going to attempt to share my screen. Hope I'll have some luck. Okay. How's that going?
Yeah, it's now visible, Professor.
Okay. All right, let's see. Okay. Um, anyway, I hope you can all see my screen now. Big data algorithms. Yes.
Yes, Professor,
Uh,
it is visible.
yeah. Can you see the people on the side? I'm going to try to get rid of that. Well, um, okay. Uh, okay, I'm going to talk about three algorithms, which you saw in the opening slide. Um, these are the three algorithms use hashing in some way. Um, that's sort of a coincidence, but I realize I'm not just talking to computer scientists. I assume that's correct, right? Uh, so I'm going to start with a brief explanation of what the general idea of hashing. Um, but well, of course, as with all algorithms, we would like to make sure that the algorithms we invent are more efficient than what you might think of as the obvious approaches, and that's true for all three of these algorithms. And something that is somewhat unusual is that the three algorithms also, they only produce approximate answers, but the more work you do, the more accurate your answers become. And then this actually is becoming a much more common phenomenon in modern algorithms. Okay. At any rate, hashing originally was designed. Actually, it was a fellow by the name of Wes Peterson in 1950. So this idea is getting very, very old. It's very important. Um, the purpose of hashing originally was to maintain a set of items. And no matter how big the set got, in an essentially constant amount of time, you could do the following. You could insert a new element, you could delete an element, and you could test whether an element was already in the set. So, for example, in the second of the algorithms that I will discuss, we're going to talk about maintaining Facebook logins. So Facebook wants to keep track of how many different people have logged in at least once in a month. And the obvious way to do it, the dumb way, would be to sort of keep a list of everybody who's logged in. So if you're the 1 billionth Facebook user to log in this month, you'd have to look at all 1 billion previous or 1 billion minus 1 previous logins to see whether that you were in fact a new user rather than someone who had logged on earlier in the month. Well, when the way a hash table works to avoid that, doing looking at 1 billion items, is you choose a function that maps the elements you're storing. For example, usernames, and it's going to think of it as throwing the elements into a large set of buckets. So there might be 1 billion buckets. Okay, and in typical applications, not necessarily true in the examples I'll give you, but the idea is to have the function sort of randomize the elements. So, for example, well, anything, character strings, any data can be represented as a sequence of bits. And a sequence of bits, in turn, is you can think of as an integer. So you take that integer, you square it, and you pick, let's say, 32 bits from the middle of the square value. And that's sort of random enough. So you can't really predict where an element which bucket an element would go into. But the key idea behind this bucketizing is that you, if let's say a new element comes in, or something you want to see whether this is a new user this month or someone that's already stored in your set, you hash it, and now that tells you what bucket it would be in if it's there. And again, if you have 1 billion users and 1 billion buckets, the average bucket has 1 element. So it might have 2 or 3, but at any rate, you only, no matter how big the set is, you only have to look at a small number of elements to see whether the element is already in the set. That's the key idea behind a classical notion of hashing. Okay, I'm going to plug my book with Yuri Leskovich and Anand Rajaraman. It's free. You can download a copy at the URL that's there on the screen. And the algorithms that I'm going to talk about today are all covered there, along with a lot more information about them and other algorithms. Okay, with that, I'm going to talk about locality-sensitive hashing. It's one of my favorite algorithms. It's an idea that appears in many different guises. For example, if you're familiar with the BLAST algorithm for stringing together short strands of DNA, that's actually a locality-sensitive hashing algorithm. was developed originally by a colleague of mine who's unfortunately passed away, Rajiv Matwani. At any rate, I'm going to again. Well, let's see the story. Okay, first of all, like hashing itself, it looks sort of like a little bit like matching, like magic. The idea is just as the classical hashing lets you see whether an element is a member of a very large set almost instantaneously. What locality-sensitive hashing does is, given a set of items, you can find the pairs of similar items without the cost of examining each pair, and that cost, of course, is quadratic. And again, if you have even 1,000,000 elements in the set, the number of pairs is about half a trillion. You can't really do quadratic things on large sets. Okay, so but just to introduce it, let's look at a very easy case. Let's define, and by the way, again, locality-sensitive hashing, I'm going to give you really a few examples, but it's a general idea. And for each notion of similarity, you have a different algorithm. But let's just define, well, first of all, we're going to play with deck of cards. And we're going to define cards to be similar if they have the same rank. Okay, so the ace of clubs is similar to the ace of hearts, for example. Think of, now, again, this is not a random hashing, but I'm going to, in fact, hash cards just into 13 buckets, one bucket for each rank. And in fact, unlike the classical hashing, you don't want a function that randomizes. You want a function that does something very specific in order to put the similar pairs into the same bucket. You have a bucket for each rank. You look at a card, you see what its rank is, ignore the suit, and throw it into that bucket. And if you do that, then what will happen, let's say all 4 aces will appear in the bucket named A, and you can then just enumerate the 6 pairs of 2 aces. Similarly for the second bucket. So you never have to even look at a pair of cards that are of different rank, because you only look within the buckets. But that's a very easy case. It's actually anytime you have an equivalence relation where similarity is defined to be equivalent according to some equivalent relation, that works. But as soon as a similarity is not an equivalence relation, you have a little more trouble. So let's say, for example, the cards are similar if they agree in either the suit or the rank. Then you'd have to make sure that the ace of clubs would be in the same bucket as the ace of hearts. And the ace of hearts is similar to the 4 of hearts because they have the same suit. And therefore, you'd have to throw the 4 of hearts in there. But this violates transitivity because the ace of clubs is not similar to the 4 of hearts. And in fact, if you think about it, in order to get all the similar cards into the same bucket, you'd have to only have one bucket, and you'd throw everything into that bucket, and then you look at all the pairs, and that's basically just looking at all the pairs. It's a quadratic process. Okay, but this is still a very simple case. And what I'm going to propose is we will hash the cards twice. Okay, the first thing we're going to do is what we did originally. We'll throw the cards into 13 buckets, one bucket for each rank. You look at a card, you see what its rank is, you throw it into that rank's bucket. But then we're going to hash the cards again. And now we're going to throw the cards into 4 buckets, one bucket for each suit. Okay. And now we have 17 buckets. And in fact, if you look at inside each bucket, every pair of cards in that bucket is a similar pair. It's important again to remember that in some sense we've thrown the cards into, each card is now in 2 different buckets. It's not hard to do that. Maybe really what you're probably putting into the buckets are pointers to the cards in practice. So there's no problem with throwing the same element into 2 different buckets according to 2 different hashings, or 100 different buckets according to 100 different hashings, as is it's a common that's a common situation in the algorithms I'm going to talk about. But okay. Again, it's if you think about it, every pair of cards that appears in one of these 17 buckets together is a similar pair. And moreover, you still never have to look at a pair of cards that are not similar, because they never appear in the same bucket. And that's actually still a little bit easier than the general case. As I said, first of all, you get all the similar pairs. If two cards are similar, they will be thrown into a bucket together. But another way that this is atypical is that if a pair does appear in a bucket, then they really are similar. Okay. Now, in the general form of locality-sensitive hashing, we're going to use some number of hashings. Again, the next example I'll give you, it's 3 hashings, but it could be hundreds. But you follow more or less the same recipe, except, first of all, sometimes you will throw two elements into a bucket together, but they're really not similar. So you have to have an algorithm that looks at pairs in a bucket and says, are they really similar or not? Moreover, in the general case, sometimes there will be similar pairs of elements that never wind up in a bucket together, no matter how many hashes. Even if you're doing hundreds of different hashings, you just never get things that fall together in the same bucket. So you get some false negatives. And again, the more hashing you do, the less chance of a false negative, but it never goes away completely in the general case. Okay, so and again, I'm going to talk about one more example of locality-sensitive hashing called entity resolution, where but in general, for any given notion of similarity, you have to come up with suitable hash functions that, well, first of all, if the items are similar, then there's a good chance that they'll be hashed to the same bucket. And if they're not similar, then there's a much smaller chance that they'll wind up in the same bucket. Now, again, this is exactly the opposite of notion of a random hash function, something that just throws things into buckets at random. Again, you might think that this is again is sort of magical. How can you design a hash function that is somehow clairvoyant, can figure out whether somehow know something about the similarity. Okay, well, anyway, I'll give you an example. You see, it's not that hard, and if you go look at the book that I mentioned, you'll see even some more complicated cases. Okay, and again, the goal of the design is you want to minimize false negatives, but there's a trade-off. The fewer the false negatives, the more hashings you have to do, and therefore the more work you'll still have to do going into each bucket and looking at the pairs. Okay, so here's how an entity resolution works. Okay, let's suppose we have a set of records, and let's say the records I'll talk about three fields. They have name, address, and phone number, and maybe other fields which I won't talk about. But the idea is that these records each record refers to a person, and you'd like to know that the notion of similarity will be that the records refer to the same person. Well, ideally, you know that it's the same person because the name fields are exactly the same, the address fields are exactly the same, the phone numbers are exactly the same. The trouble is there are both, for example, you might use your middle name in one record and not use that middle name in another record. So the names look, similar, but they're not the same exact name. So you might begin to wonder whether these are the same people. You might, move from one place to another. So the addresses, even though the records refer to you, the addresses would be different. Similarly, you could change your phone number. There could be typos. And conversely, there are people with the same name who are different people. Okay, so just because the names are the same and two records doesn't mean that they refer to the same person. What you would hope in that case is that even if the names are identical, if they're different people, the addresses would not look similar and the phone numbers would not look similar. And then, as I mentioned, if you had even a set of 1 million records, you'd have to do approximately, 1 million choose 2, which is about 500 billion comparisons. So that's a large amount of work for just 1 million records. And if you look at it, credit rating agencies, they get records about people's transactions at the rate of hundreds of millions of transactions a day. And again, it's very important that they determine who is who. You don't want, if someone with the same name as you has defaulted on a loan, you don't want that somehow affecting your credit rating. Okay, so here are the hash functions we're going to use. Again, think of it as one bucket for each possible name. Okay, and so we're going to just take the records, we'll throw them into buckets according to the name value. I might comment that in this case, we wouldn't actually bucketize things because there are in principle an infinite number of possible names, so you can't have an infinite number of buckets. What you do is sort the records by name, and then all the records with the same exact name would appear together, and you just peel those off as one bucket. Well, we might then do another hashing based on the identical having identical phone values, one bucket for each possible phone, and then a third hashing, let's say, on the address field. And again, ideally, we would like to know that if two records do represent the same person, then they'll, at least in one of those three hashings, they'll wind up in the same bucket. Okay. And the savings come from the fact that if if two records refer to different people, then there's a good chance that they won't have the exact values of name, exact value of address, and exact value of phone. It could happen. For example, if you're, two people sharing an apartment would have the same address, but they're different people. So you get some, some problem in a bucket where things do get hashed in the same bucket, but they're not really referring to the same person. But the savings comes from the fact that any two records that don't agree in any of those three fields never wind up in the same bucket, and therefore you never have to consider them at all. And that's the big win. Okay, and as I said, for a variety of reasons, two records will sometimes get thrown into the same bucket, but they do not represent the same person. So, for example, two records referring to two different people with the same name will wind up in a bucket, but presumably when you look at the phone number and you look at the addresses, you'll say, oh no, these are not really the same people, the same person. Okay. Well, again, just to summarize, you will you hash all the records several times based on common fields that all the records have, and then you only compare two records if they have been thrown into the same bucket for at least one of these hashings. And as I said, you do get false negatives because you could have conceivably two records that do represent the same person, but there are typos, or or you in one record you put your landline and another your cell phone, so the phone numbers don't match. It could happen, and in fact, in practice, does happen. Okay, with that, I want to talk about the next another interesting problem, an interesting algorithm to solve it. It's called counting distinct elements. Okay, and remember, I talked about, well, I find it useful to think of the problem as there's a data stream of elements. Now, if you have a fixed set, you can just make a stream out of it by just listing the elements of the set in any order you like. But it's most useful when you think of it as data is coming into you at an unpredictable but very high rate, and your job is to count at any time. You have to count the number of distinct elements you've seen so far. So two examples, for example, Google gets search queries. They come in from all over at an unpredictable rate. And Google deals with each as it comes in. And again, I want to talk about the Facebook logins problem again, where people log into Facebook, and it's you get the stream of logins, and Facebook has to count how many distinct logins there are. Again, someone may log in many times in a month. You don't want to count them more than once. And at any time, you have to know how many different elements you've seen up to this point in the stream. So again, there's the dumb way to do it is you just maintain the set of elements that you've seen. So, for example, Facebook could keep a hash table, which is the thing I really started talking about at the beginning of this talk, where you throw every time someone logs in, you keep that user's login name in the hash table. Then it'll be in one of maybe a billion different buckets. And on the side, you keep a count of the users that you've seen. So when someone logs in, you hash it to the table. You have to look only at the bucket that it hashes to, and that again, even if it's the billionth user, you only have to look at the users in its bucket to see if it's new or if it's already in the table. If it's already in the table, then you do nothing because it's not the first time this person has logged in this month. On the other hand, if you've never seen it, then you add it to the table, in particular to the bucket that it hashes to, and you increment the count by one. And this works. The problem is uses a lot of space. And again, Facebook has, I don't know, something like 3 billion users in a month. And so, a terabyte these days, not that enormous. Facebook, no problem. But it is a significant amount of space. I want to give you another example application where the hash tables themselves don't grow, aren't large, but there are maybe 1 trillion different tables that you have to store. So compressing the table is a real value. The story that I want to talk about now is what's called a web crawler. Again, Google probably every day crawls the web to see what's out there, visit all the pages. And it starts from some number of root pages, which might be, for example, the home pages of universities all around the world, maybe a couple of hundred different universities. And you crawl the web. Well, when you find a page, you look at all the links on that page. You report those links to some central server, and eventually each link is looked at. That you follow the link and you see what that page is. You find its links and report those for possible examination. The interesting thing is that the web is so large that even Google can't look at the whole thing. So it might, for example, go out, I don't know, 12 hops. That is, get every page that you can reach from a university homepage, following at most, following it up to 12 hops. At some point, though, it's got to start, saying, well, if a page is so obscure that you can't get to it in 12 hops or 15 hops or something, probably nobody wants to see it anyway. But well, we'll look at a couple. We'll look just at least check to see if there's anything out there that's a little bit popular. Might be the answer to some search query. Okay, now, if you know how Google works, there's this notion of page rank to actually represent the popularity. But you can't compute the page rank until you have the whole web in front of you. So you might estimate popularity by just how many different predecessors, how many different pages link to this page, to decide, if it has at least 5 predecessors, then I will crawl it, look at its links. But if I don't find 5 distinct predecessors, then I'm not going to look at it. I might comment that, again, the server that's counting how many predecessors a page has, again, you may get the same predecessor more than once because you have many different crawlers that are working independently. Two crawlers or more may eventually find they might find the same page, report its links back to the central server. So sometimes you'll get a link, more than one link to the same page. So you really have to count distinct predecessors, not just how many times a page is reported. Now, again, the algorithm I'm going to describe, this is the Flageolet-Martin algorithm, it gives you an approximation to the count. Again, the more work you do, the better, the more accurate you count. But in this case, we're sort of guessing which pages we want are the best ones to crawl anyway. So an approximation should work just fine. Again, what I'm offering is a way to save space compared with the idea of just hashing all the elements you've seen into a big hash table. And in this case, as I said, you're counting the number of predecessors of trillions of pages. So even 10 bytes per 10 bytes per page, and that's, you can't really do a hash table in as little as 10 bytes. That's a petabyte. You just don't have the space. So as I said, the Flageolet-Martin, it just estimates the count. And the way Flageolet-Martin works is you pick a hash function, and well, actually, it uses many hash functions, probably several hundred in the general case. I'm just going to describe one hash function. And now, by the way, this is a classical hash function, something that really does randomize things. Unlike the hash functions that we used for locality sensitive hashing. Okay, so again, a hash. Okay, we're just going to talk about one of the hash functions. I'll assume that if there are n elements or up to n elements of the set, then you need at least log base 2 of n bits. And for this hash function h, I want to let we'll call the tail length of any element in the stream. Let's say it could be a URL if you're web crawling, or it could be a Facebook login name. If you're counting distinct users. Okay, we'll just let little r of a is the tail length of the number of trailing zeros. So for example, the bit string 000101 has a tail length of 0 because it ends in a 1. That is no zeros. But 101000 has a tail length of 3 because it ends in 3 zeros. And now for this hash function h, I want to record r, capital R, to be the maximum tail length that has been seen for any element in the stream. Okay. Okay. And I might comment that, certainly for the application of counting predecessors, 4 bits is plenty. That lets you 4 bits lets you count up to 15. If something has 15 distinct predecessors, you really want to crawl it. But the point is that based on this capital R for the hash function, the estimate that I'm going to give for the number of predecessors is 2 to the power R. And now, why does that make sense? Well, it doesn't. But let's see the argument. Okay, if I have seen 2 to the R different values, okay, then there's a good chance that I'll see one that has R zeros at the end. There's the one with have a tail length of R or more. The probability is actually 1 minus 1 over E, or about 69%. On the other hand, if I've seen many fewer than 2 to the R different values, then there's a smaller chance that I will see one with a tail of R. If it's a lot smaller than 2 to the R, then the chances are just that number over divided by 2 to the R. Okay. There is a little glitch, however, which is that in principle, you could argue that the expected value of 2 to the R is infinite. And what happens is an occasional very long tail will throw off the estimate. You just get something that's outlandishly large as an estimate. And so at least for when R gets large, the probability when you go from R to R plus 1, the probability of seeing a tail of that number of zeros will roughly halve. On the other hand, the estimate you're using will double when you go from R to R plus 1, and therefore every possible value of R is contributing the same amount to the expected value of the estimate. And so what happens is, sometimes you won't get an outlandishly large value of cap R, but if you take a large, again, if you take a large number of hash functions, you can think of it as maybe hundreds of different hash functions. You want to sort of get rid of the outlandishly large estimates. Again, if you just happen to get an unusually large value of R, it just throws the calculation off. So we're going to use, let's say, hundreds of hash functions, and then we're going to combine them in some way. Again, average doesn't quite work because again, just because the average is in principle infinite. And what it means in practice is if you happen to get something that's very large, an R that's very large, it just throws the whole average off. We can take the median, and the purpose of a median, of course, is to get rid of the extreme values. The trouble is, of course, since each estimate is a power of 2, the median of your samples is going to be some power of 2. Okay, so if the true value, let's say, is 100, you're going to get 64 or 128. No matter how many hash functions you use, you're never going to converge to 100. You'll either get 64 or 128. Well, there's a simple way to handle it. You group the hash functions into small groups. You take the average within a group. And if you take something like 4 log n, where n is the number of elements, then that's sufficient so that you could get an average that's any number. It won't necessarily be anywhere near a power of 2. So you can take the average within the group. The trouble is, of course, that, again, a group, a group that happens to have some very large value of cap r, it'll throw, you'll get an outlandishly large estimate. But then, since you have several groups, you take the median of the averages, and that will get rid of the outliers, the crazy large values. Okay, so the last story I want to give you is sampling a stream. We'll see the story. First of all, as with the other examples of algorithms I've given you, there are easy cases. So let's suppose that Google wants to look at a stream of search queries and find out how many times the search query Taylor Swift was asked in a month. But we want to sample. We're going to take a random sample of the search queries, say 1/10 of the actual search queries, and we're only going to look at the sample. Okay, just obviously, it will save time because we're only looking at 1/10 of the search queries. So you just count the number of occurrences of Taylor Swift in the sample and you multiply by 10. Since even the sample now is billions of search queries, statistically, you're going to get an estimate that's very accurate. Okay, and that's the good case, very easy. But now let's consider something that looks rather similar, but in fact where the easy approach just doesn't work. So what Google wants to find out now is how many unique search queries were there? That is, things that were asked exactly once in the stream of this month. But again, we'd like to just sample 1/10 of the stream at random, and then maybe adjust our value, adjust the result to get the true answer for the whole stream, or at least a very good estimate of it. The trouble is that in the sample, you're going to see unique queries, things that look unique but really aren't in the whole stream, and moreover, there's no relation really between how many unique queries you see in the sample and the number that are unique in the whole stream. So again, let's suppose it will take a 10% sample of the stream. If a query is unique, it's got a 10% chance of being in the sample. The trouble is, you're going to get things that look unique in the sample, but really come from some query that isn't unique. So if a query occurs twice in the stream, there's an 18% chance it will appear exactly one of those two occurrences will be in the sample. If it occurs 3 times, there's, I think, a 24% chance. The point is, you're going to get unique queries in the sample that have nothing to do with the that somehow don't connect to unique queries in the whole stream. Unlike the Taylor Swift case, where every time you see Taylor Swift in the sample, it came from a Taylor Swift query in the whole stream. Well, it turns out we made a little mistake. Okay, we sample based on the position rather than the value. So in this case, if I want to estimate the number of unique queries by taking a sample, I'm just going to hash the search queries to 10 buckets. Okay, and then I'm going to my sample will be one of those buckets. Could be any of the 10 buckets. Let's say it's bucket 0. Again, because this is a classical hashing, so it goes the search queries are sent randomly to one of these 9 buckets. So each of the buckets should have a typical number of unique queries. At any rate, so we'll take this sample to be the queries that hash to, say, bucket 0. And the important thing then is that since the hash function depends only on the element itself, on the search query itself, either all or none of the instances of a given search query will go into bucket 0. And therefore, if we just examine bucket 0, we would expect the expected value of the fraction of unique queries in the sample is exactly the same, or should be. Well, it's a good approximation to the fraction of unique queries in the sample as a whole. Well, let's see. If you can even do more with this approach. So suppose that we want to limit the sample size. We're going to say, well, I'll take 1/10 of the stream, but if the stream gets too big, then I want to cut down my sample size. So you don't have to just hash 10 buckets if you want 10%. You could say hash to 100 buckets. Okay, and initially you want 10% sample, so take buckets 1 through 9, or any 10 buckets you like. It doesn't matter. On the other hand, if the sample gets too big, then you could just throw out bucket 9. And if it's still big, you get rid of number 8, and so on. Well, now you can get a sample that eventually you get a sample that's only 1/100th of the stream. But if that's your constraint, then fine, just do it. Well, I want to just finish up by giving you the trick. Okay, what you want to do is you want to see your data as pairs, key value pairs. Now, the key, again, I don't know how many of you know the programming language SQL, the query language SQL. If you do, the key is the attributes that you find in the group by clause. If you don't know SQL, the idea is this. You're asking a question about some in which you're grouping the elements of the stream in some way. For example, in the unique finding the unique queries, what you're really doing is you're grouping the stream by the value of the element itself. So you have one group for each possible query, and the question you were asking is that group of size 1? That is it actually a unique query, or is it or is the group larger than 1, in which case it's not a unique query? Okay, well, so actually in both of these examples, the data was all key. You didn't see the value. But I'll give you a more complicated example where there is a non-trivial value key distinction. Okay, so you want to hash the keys to some number, only the keys to some number of buckets. So what you get, again, the sample will have all the key value pairs with certain of the keys. Okay, and what that means is you get all or none of a group. And again, that was how we solved the unique query problem. And I want to just give you very quickly an example, a more complicated example. In this case, the data elements of the stream are triples consisting of an employee ID, a department, and a salary. Okay, meaning that the employee works for that department, and the salary is such. And the query I want is what is the average over all departments of the range of salaries within a department? That's the high salary minus the low salary in that department. So we're obviously, if you think about it, we're grouping by departments. The question that we're asking has to do with for each department, the set of employees and their salaries in that department. So the key is the department, and the value is the employee ID and the salary. And again, if you picked random tuples, triples, that is, if you mistakenly picked your sample by picking random positions in the stream, then for each department, you're going to miss a lot of the minimum and maximum salaries. Or most departments, you'll miss either the minimum or the maximum. And unfortunately, that the bias would always be to the low side. That is, you're looking for the range, if the range of salaries in the department, and so that what's really only important are the minimum and maximum salaries. If those are missing for a department, you always get something too low. You can't get something too high. So again, you can't pick random tuples. You have to pick random departments. Okay, but if you pick a sample based on departments, that is, you get all for each department, you get either all or none of the salaries in that department, and in particular, you'll get the minimum and maximum salaries. Okay. Anyway, thank you very much for listening. And with that, I will.
Yeah. Thank you very much to Professor Uman. Now, I would like to take a few questions so that the participants can ask. So if there is any question, please go to the react button, and there is a raise hand button. So just click it, and once your hand will be raised, so you will be allowed to ask question to Professor Ullman.
Okay. Let's see. I see a hand up.
Okay, actually, I'm not 1 minute.
Abhay Sharma.
Okay. Yeah. 1 minute. I'm allowing. So, yeah.
Hello.
Yeah, Dr. Abhay Sharma. So you please ask question to Professor Ullman.
Hello. First of
Hi.
all, this opportunity to be able to. Hello.
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 Yeah,
Yes.
you are audible. You are audible.
Yeah.
Okay, sir. I can't believe that I am talking to you. So, my question, sir, is that in order to pursue a PhD in theoretical computer science, how much of mathematics is required? Like, do you need very hardcore mathematics or?
These days, a lot more than I know. I if you look at the really good work in theoretical computer science, it uses a lot of remarkably deep mathematics. So I would.
Okay.
Yeah.
Okay. So thank you, Dr. Abhay. Now I would like to unmute Professor Guru DS, who raised hand. So Professor Guru DS, so you can ask your question to Professor Ullman. Professor Guru DS, so
Yes,
please.
you're on mute. There
Can
we
you
go.
can you hear me, please?
Yeah,
Yes, we
you are
can.
audible.
Yeah. Good evening and good morning to Professor Ullman.
Hello.
I'm Professor Guru from University of Mysore.
Mhm.
So I've been referring your books on automata, formal languages, and I still have a copy of your old book on formal theory of languages from grammar to automata,
Mhm.
the old
Right.
version. I enjoy reading even
Yeah.
your 2 volumes of books on databases, database management systems,
thank you.
volume 1, volume 2. My concern is, could you just highlight a couple of concepts like ensembling of hashing with reindexing and ensembling of hash function with hash function, so that it would speed up the search process, right?
Wait. Are you talking about
Huh.
sort of the classical hashing, that there are some tricks?
Correct.
Yeah. Yeah, I must admit, I never worried too much about that, because if you pick the number of buckets wisely,
Even individual bucket could be too big.
yeah, that's well. First of all, you can rehash every once in a while.
Yes, yeah.
Okay.
But instead of rehashing every key value, can we think of sub-hashing within a bucket, or we can create a very balanced tree structure so that.
Okay, I don't know if everybody's getting the idea of what we're talking about, but suppose that let's say I have 1 billion elements and I'm going to take 1,000 buckets.
Correct.
Okay, then you're going to get 1 million elements in one bucket. That's still a lot to go through.
Yeah, that's still a big data.
You can use another hash function.
Yes.
To hash that bucket.
Correct.
Into
so that we'll think of
1,000 ways.
Yeah, we'll think of multi-level, hashing.
Yeah. Yeah. I mean, on the other hand, I could also just start off by hashing to 1 million buckets.
Okay.
And the amount of space would be, in fact, would be a little bit less. It's more or less the same anyway.
Okay.
Yeah. So I'm not. I mean, there might be some applications of that approach.
Correct. There are quite a good number of applications, especially in image retrieval.
Yeah. Okay. Yeah. Okay. Fair enough. I guess it has to do with the first hashing might be, I don't know, on an average blue or something like that, and then within that you hash on average red. So the hash function itself is easier.
Okay.
Right. Yeah. I don't know. I mean, I'm sure there's some interesting things.
Thank
to
you.
Do there.
Thank you very much.
Thank you to Dr. Guru DS.
Yeah,
So
thank you.
Professor Ullman, I have one question to you. So right now, people are trying their level best to do the big data analytics or big data analysis with the help of the small data from the big data. Now the question is that there are several works are going on in this field. Okay, so I personally believe that technique will not be fruitful, because if we are uh, dealing with the big data and taking the small data from it and doing the data analytics and telling it's a big data analytics. So what's your opinion on that kind of methodology?
Well, wait, are you talking about sampling?
Not exactly something, but
No,
doing the
yeah.
analytics field using the big data.
Right.
So because as
Well,
you know that when we deal with the big data, so big data has the several characteristics, and that characteristics must be preserved for the big data. But when you would take the small data out of that one, so it becomes a static data, and its characteristics are losing. So how can we say that we are doing the big data analytics? That's my question. So
but I mean, I thought again, it sounds like you're talking about sampling, which is exactly the problem I was
hmm,
um, saying. And I mean, you have to do the statistics, but if you're, again, and I hope that the last of the three stories that I gave you it suggests some of the pitfalls
hmm,
where when you take a sample, it's not sometimes representative of the data set as a whole, and yeah, so you have to be very careful how you uh, how you take your sample. And I tried to give you one important idea, uh,
exactly.
you know, to avoid a pitfall.
Okay. Thank you,
Um,
Professor.
but again, even a sample, again, if you take 10% of the search queries that Google gets in a month,
Mhm.
you're still talking about billions and billions of queries. And the statistics when you have a billion things, statistics tends to work. Okay. Again, unless you've made some mistake that forces a bias, like throwing away minimum and maximum salaries that I gave you, you're going to get something that's remarkably accurate. Okay.
Okay.
Um,
So, okay, thank you, Professor. Professor, last question from Mr. Kiran. He is probably here. He is asking that how far big data theme useful in paleoclimatic, sorry, paleoclimate studies, especially rainfall estimation. What type of algorithms that you can suggest to have high quality or reliability results?
oh, gee, I know nothing about paleoclimate. Barely know the weather today, but I think you really have to be much more specific and tell me what question. I
Okay.
can't give you an algorithm until you tell me what question
Okay. Actually, it
you're
was a
asking.
question, Professor. So
Professor,
anyway.
can I talk now, if possible?
Yeah, Mr. Kiran. Yeah, Mr. Kiran, you please
Uh-huh.
continue.
Yeah.
But take very less time. Okay.
Yes.
Okay, sure.
So just to estimate some 1,000 years back climate patterns, so that we can assure the future food securities, those data to estimate climate, and that to make sure some food security analysis for that purpose only.
Um, well, again, that's not a question I can answer, right?
Okay. So
Okay. Okay.
Again, if you give me a you know what question, what does your data look like? What kind of a question do you want to
the
tease
data is
out?
data is mostly on basing of the remote sensing and somewhat related to literature. We're basing on both these data.
Yeah.
Because we don't have so many gaps both in these patterns. That's why how to achieve the reliability qualitative way. That's why.
No. But you're talking about the climate 1,000 years ago, so presumably it's not just remote sensing. You're
Yes, sir. Those are some
looking at ice cores or something like that, right?
Those are basing on available from the rock materials, some literature review, like that only, and somewhat by remote and comparing with the present remote sensing data. So that is as to try to make sure some estimation, so that we know how far it is going to affect in future, so that how to make some strategies for the food security, agriculture, like production, like that, sir, for that purpose.
Okay, so um, uh, okay, so it sounds like you're probably looking at a sequences, right? Of I don't know, month by month average temperatures or something like that
Yes, sir, something I said.
at a given location. So you want, um, yeah. So you have, um, I mean, okay, what do you do? You probably want to fit a curve through the data.
Yes, sir. Yes, sir. Yes, sir.
But I guess uh, you're making the look. You have to make some sort of an assumption. For example, fit a cubic polynomial through your data. Okay, there are algorithms for it's a basically regression algorithm. You get the best cubic polynomial, let's say, through your data, and you have to, but uh, you then have to justify that that this trend is intact, and you never you never know that's the case. I mean, um, I think we all, rational climate scientists, believe that the Earth is warming, right?
Okay.
So
So
the trends that you see are going to remain intact for the next century or so, unless we do something about it. Okay, so again, fitting some sort of a reasonable curve. Uh, I don't know, cubic, put a straight line through it. It's probably pretty reasonable. You can't. The trouble, of course, is in climate. There are these theories about. I forget the exact term, but um, you basically get these state transformation. We talk about what happened. At least in the United States, we think about what's called the Gulf Stream, the warm water that goes from the western shore of the Atlantic, actually heads toward Europe, which it warms England, for example. That is in danger of stopping, and if it stops completely, then your previous data doesn't. You just might as well throw it out the window, because you're suddenly in an entirely different regime. Okay. And I assume that climate scientists are working very hard to predict that issue, but when it does, you can't just, if something like that is going to happen, you can't just fit a straight line or a quadratic or cubic or something.
okay, thank you, Professor Woodman.
Thank you, Professor.
So I'm requesting all the participants to please not ask too many questions right now, because we are not entertaining any more questions. It's more early morning in the USA. Now it's time for vote of thanks. So, Honorable President of the Indian National Science Academy, INSA, Honorable Chairperson of the Indian National Young Academy of Science, distinguished speaker, eminent guests, and dear participants. As the co-editor of this INYAS distinguished lecture, it's my privilege and honor to propose the vote of thanks. At the outset, I offer my deepest and most sincere gratitude to Professor Jeffrey David Ullman, Emeritus Professor, Department of Computer Science, Stanford University, for delivering an exceptionally enlightening and inspiring lecture. His pioneering contributions to database system, big data, and related areas have profoundly influenced the field, and his insightful address today has greatly enriched all of us. We are truly grateful for his time, generosity, and gracious acceptance of our invitation. I express my heartfelt thanks to Honorable President of Indian National Science Academy, Professor Shekhar C. Mandesar, for his visionary leadership, encouragement, and continuous support in enabling the successful organization of this distinguished lecture. My sincere thanks to Dr. Mohit Tyagi, Chairperson of Indian National Young Academy of Science, for his constant guidance, motivation, and unwavering support throughout the planning and execution of this event. I also extend my thanks to all the staff members of INYAS and INSA for their valuable support and encouragement. I'm deeply thankful to all distinguished fellows, members of INSA and INYAS, and eminent personalities from academia and industry for their gracious presence and encouragement. I would also like to acknowledge with sincere appreciation the enthusiastic participation of researchers, scientists, scholars, and students from various institutions across India and abroad. Your presence has truly made this event meaningful and successful. I would like to place on record my appreciation for Ms. Ananya Banerjee of INIAS for her constant support in managing various official communications related to this program. My special thanks goes to Miss Ria Sejal Sharma, my PhD scholar, for various data and typing related support. Finally, I extend my heartfelt thanks to each participant for your valuable time, active engagement, and continued support. With these words, I conclude the vote of thanks. Thank you all. So thank you all
Well,
for
thank
joining
you,
us.
Shantanu. Thank you. Thank you. The honor is all mine. I think
Thank you,
it's
Professor
a
Uman.
wonderful opportunity to talk to the next generation of the world's leading scientists. I thank you for the opportunity.
Thank you, Professor.
Hmm.
Thank you. Thanks to all.
Okay. Okay.
Thank you.
So,
Yeah, Professor, now we can leave